This example is again an example of a one unit non-reactive system, but we're going to put more of an emphasis on how to choose a solution path. So this is going to be a little bit more complex and shows us the power of drawing the table of the balances and unknowns. So first of all, the question says an air humidifier evaporates water into dry air. The incoming air has 21 mole% oxygen and 79 mole% nitrogen. The humidified air has 20 mole% water vapor. Calculate the volumetric flow rate of liquid water needed to humidify 500 pound moles per minute of dry air. So first we'll draw our humidifier. So first thing is we'll draw out our system. So we have a humidifier. And we're told we have two streams coming in, right? We have a dry air stream and we have liquid water that gets evaporated. So two streams going in and one stream of humidified air coming out. Now the dry air has 0.21 pound moles of oxygen per pound mole and 0.79 pound moles of nitrogen per pound mole. And this is just going to be liquid water. And the stream that's coming out, we're told that it has 0.2 pound mole water vapor per pound mole. And that's basically what we're told. We're asked to humidify 500 pound moles per minute of dry air. So this will be 500 pound moles per minute. And now we'll mark the rest down as unknowns. So we don't know how much water is coming in. So we'll mark that as NW. And this is going to be in pound moles per minute. And I'll talk about that in a second. Here, we don't know how much product we have coming out. So we'll call this NP, also in pound moles per minute. And we'll mark XO2 as the fraction of oxygen in the humidified air. So that'll be pound moles of oxygen per pound mole. And we know that the sum of the mass fractions has to equal 1. So if we do 1 minus 0.2 minus XO2, we have 0.88 minus XO2 pound moles of nitrogen per pound mole. And we know that these have to be in here because they're coming into the system and there's no reaction in the system. Therefore, if you have nitrogen going in, it has to be coming out in the product stream. Now let's talk about why do we use units of pound moles per minute for the liquid water stream when we're asked to calculate the volumetric flow rate of the liquid water needed to humidify this air. First, let's take a look at what our basis is, okay? So the question asks us how much of this water you need to humidify 500 pound moles per minute of dry air. So we're gonna take 500 pound moles per minute dry air as our basis. And because our basis is in pound moles per minute, it makes more sense to select units of pound moles per minute here and then do the conversion to volume later. Now, in terms of the basis, you could also select if you wanted, even though you're being told that you're being asked about 500, because there's no reaction here or anything complicated, you could select 100 pound moles per minute and then multiply the result by 5. But there's really no reason because 500 pound moles per minute is a pretty convenient basis anyway. So now we'll draw our table of balances and unknowns as we always do. So balances and unknowns. And again, we always have the total balance, whether it's mass or mole or whatever we're using. So total balance. And here we have three species, right? We have water, oxygen, and nitrogen. So we'll write H2O, O2, and N2. And it's important to note that even though the water coming in is liquid and the water coming out is vapor, it's still the same species, so it only has one independent balance. Now, our system again is the humidifier. So we have to see what's coming in and what's going out. So going in, we have 500 pound moles per minute of dry air, so everything's known here. We don't know how much water is coming in. We don't know how much product is coming out. So here our unknowns are NW and NP. Now if we look at the water, there's no water in this dry air stream. We have NW in the incoming water, and we know the mole fraction of water, but we don't know what the total here is. So again, NP. And then we go to oxygen. We know everything about oxygen here. There's no oxygen coming in the water. And for oxygen here, we don't know the mass fraction and we don't know the total flow rate. So we have NP and XO2, and the same thing with nitrogen. So we have NP and XO2. And now this is where this question differs a little bit from previous questions that I've shown. You wanna keep in mind after you draw your table of balances and unknowns, what am I being asked to calculate here, right? So we're being asked to calculate the flow rate of the liquid water. So basically we need to find NW. Now, if we did a total degree of freedom analysis over the system, we'll see that we have three unknowns, NW, NP, and XO2, right? So three unknowns. And we have three species, so we have three independent balances, right? Minus three independent balances, which would be O2, N2, and H2O are the species that give us those balances. So you could, in theory, if you wanted, solve the entire system. So you could start, for example, by solving oxygen and nitrogen simultaneously and getting a solution for NP and XO2, and then plugging in NP from here into either the total or water balance to get NW. But there's really no need to do that, right? You're only asked about NW, and you can see that if you did the total balance and the water balance, you would be able to solve simultaneously for both NW and NP, which would give you the solution. So in this case, you're gonna completely ignore the oxygen and nitrogen balances. And that's the importance of drawing this table out so that you can focus on what you're really being asked to solve. So what I'm gonna do is I'm gonna, again, start with the total mole balance and then the water mole balance, and we'll solve them simultaneously. So total mole balance, A equals I minus O plus G minus C. This is steady state, non-reactive. So what goes in must come out. We have 500 plus NW equals NP. That's our first equation. Now we do H2O mole balance. Same, A equals I minus O plus G minus C. No reaction. Steady state. Input equals output. And then coming in, we have NW. It's nothing in water going in here. And then going out, we have NP times 0.2. Okay, and this is our second equation. So we'll solve these two simultaneously. Basically, we're just gonna take NW from here and plug it into this equation. So 500 plus 0.2 times NP equals NP, or 0.8 NP equals 500. And finally, NP equals 625 pound moles per minute. Of course, keep track of the units when you're solving these. I just want to be efficient in solving now, so I'm not writing out all the units like I did in previous examples. And we have NP, but that's not what we're looking for. We're looking for NW. So we'll go back and solve equation 2. NW equals 0.2 times NP. So 0.2 times 625 equals 125 pound moles per minute. And this is liquid water. But we weren't asked to find the molar flow rate of the liquid water. We were asked to find the volumetric flow rate. So we'll use some conversion factors. So we take this 125 pound mole water per minute. The molecular weight of water is 18.02. So 18.02 pound mass H2O per pound mole H2O. So these cancel out, and then you can use the density of water, which you can find online or in different books. And we're going to use units of pound mass per cubic feet for this. So every cubic feet has 62.4 pound mass of water. So these cancel out, and it ends up that you need 36.1 cubic feet per minute of liquid water. So again, the whole point of this example is to show that once you draw the balance and unknown table, you should ask yourself again, what am I being asked to find? And then map out the way to do the solution in the simplest manner before you start writing out the balances. Hey guys, hope you enjoyed this video. If you did, please subscribe and turn on notifications for the next videos. If you have any questions, leave them in the comments and I'll do my best to answer them. And I'll see you all in the next video.